Welcome to part 4 of the tutorial. This section is going to be about implementations, talk about some experimental results, and finally we'll conclude with some open problems. So although all the experiments I'm going to be showing you here were run by either Francesco or I, you don't have to take our word for it that this algorithm is good. So here are other people. For example, one person has won a Kaggle competition actually using some of these parameter-free algorithms. So they used the COCOB parameter-free algorithm to train some deep learning models to achieve very good results without having to tune their learning rates. This, of course, provides some foreshadowing of the fact that we will, in fact, be able to see some good results later on deep learning. But for now, I'm going to focus on convex regression tasks, just because that's where we have our strongest theoretical bounds. So we're going to look at a bunch of data sets from the OpenML repository. And we're going to filter for data sets that have large numbers of examples and large numbers of features. So we want the larger data sets. Each data set specifies a linear regression problem. So we're going to minimize the absolute loss by just regressing linearly each feature to try to predict the label. We're going to compare the parameter-free algorithm Pistol, which is available in Wabbit, to AtterGuide and SGD, which are also in the same library. So you can try these algorithms out yourself if you just download the library. Pistol uses per coordinate updates. It guarantees the regret bound that sums over all the coordinates of norm of xi star times the square root of sum of the gradients. For AtterGuide and SGD, we're going to sweep the learning rate data. So both of these algorithms take a learning rate parameter, sort of a base initial learning rate, and we're going to plot the test loss as a function of the learning rate. Pistol does not have a learning rate, so we're going to just plot it as a straight horizontal line on all these plots. And I'm just going to go through a bunch of data sets here and show you the plots, and we can discuss a little bit what's happening. So here's the first one. It shows sort of the right characteristics that one might expect, which is that for AtterGrad and SGD, things get a little bit worse if your learning rate's too small. If your learning rate's too big, things are also worse. Back here, they're catastrophically bad. And there's some kind of Goldilocks just right learning rate in which you get the best performance. Pistol is a flat line, as I mentioned, because there's no learning rate. And in fact, in this case, it actually outperforms everybody, even at the best value. Here's a different data set. You have a similar story where there's, again, one single best learning rate. And if you are too small or too big, things are worse. Here, you can get slightly better than Pistol, but it's pretty marginal. In fact, it's less of a gap than we saw on the previous slide. Here again, a similar story. You can be too small, you can be too big, you can be just right. Same thing here as well. I'd like to point out, though, one other thing to notice is that the Goldilocks learning rate for AtterGuide and SGD has been moving around, right? So here, it's about 0.1 is the right value for the learning rate. But just to look at the next plot here, the right value for AtterGuide's learning rate is about 100. And if you tried 0.1, or tried 1, sorry, it would be quite poor. And SGD, if you tried 1, it would be a total disaster. And you have, it doesn't really matter, maybe once you're below 0.01, but the learning rate has to be in the smaller regime. The next data set, we see a totally opposite story, right? The first one, we had 1 as learning rate. Here you have to be AtterGuide, it has to be around 0.1, and SGD has to be around maybe almost 0.01, right? And finally, one more. Now, AtterGrad, you want to be around 1,000 as your learning rate. And if you were at those smaller learning rates, you'd actually be doing quite a bit worse. SGD, again, now it's around 1 again, but if you pick these larger or smaller learning rates, things are quite poor. So here again, it's the same story. Again, 1 was perhaps a good learning rate here on this particular data set, perhaps, but we still see that there's a lot of sensitivity. And finally, there are some data sets where actually, no matter how you tune the learning rate, you do way worse than Pistol. So in the previous ones, there was maybe not a huge difference, but here you can see that this is the first time there's actually been a gap, and Pistol is actually the winner. So what are the takeaways here? I think the most important one is that this is not just some theoretical quibbling. This actually works, right? You can implement this algorithm, and you'll see very good results. The second is that there's no common default learning rate that works for all the data sets. I think it would have been pretty reasonable to believe that real world problems are somehow very regular in some way, and as a result, there should be some default learning rate that will do pretty well, at least on all of them. But that didn't seem to be the case, right? Things that were good on one data set were actually catastrophically bad on other data sets. So the world is not quite as nice as we would like. And finally, sometimes the parameter-free algorithms can outperform the tuned gradient descent, sometimes by quite a lot, right? And that's interesting because you might have thought that by our sort of theoretical analysis, well, we're only matching the guarantee of gradient descent. But that's not quite the whole story, right? Remember that using the per coordinate updates, sorry, it seemed like we were actually getting some nice sparsity adaptivity that really wasn't possible with gradient descent. And we'll come back to this theme later on to show that there are other scenarios where we can get parameter-free algorithms whose bounds actually outperform any tuned gradient descent. All right, so let's move on to talk about deep learning, right? Nowadays, if you want to get really the best possible performance on some task, everybody uses some deep learning model. Unfortunately, this seems bad because our theoretical analysis really relies on strong global convexity properties, right? Even more so than perhaps SGD or Adagrad type analyses. There, the updates are kind of very local. You can think of it as making some sort of almost proximal style of thing. Whereas here, we're really relying on the fact that the gradient at any given point tells you something non-trivial about the loss at the origin, and that's not true for convex models. But we can just try anyway and see what happens. And it'll turn out that we do have to make some small tweaks to get the best performance. I'm going to describe for you what those are. That said, of course, because of this, providing solid theoretical foundations here is a really good open problem. Like what things can we do with these parameter-free algorithms? What tweaks are the right tweaks to make, and so on. So I gave some intuition that we're using these global convexity properties, so maybe it's a bad idea. Let me give some intuition to say that it might actually be a reasonably good idea as well to use parameter-free algorithms for non-convex models. So this is going to recall some argument that Francesco presented in section 2. Let's remember that the optimal gradient descent tuning looks like a learning rate with norm of x star over g root t. And let's see what happens if we use betting. So the typical coin betting fraction actually tends to end up looking something like 1 on g root t. Not exactly, of course, but that's roughly what it ends up being. And supposing that we have a 1D problem with x always positive, then if we were to use this particular betting fraction all the time, we would end up with a algorithm that looks like the following, right? Xt plus 1 is beta times the wealth. We can write that as beta wealth t minus 1 minus beta gt, which we can then write as xt minus gt norm of xt over root t. So what this is saying is that parameter-free algorithms behave similarly to gradient descent with learning rates equal to scaling by the magnitude of the current iterated xt. And in some intuition, this is saying that, oh, I'm using the xt as a proxy for x star when computing the learning rate somehow. But actually, we can also draw connections to recent heuristics for deep learning, which has been observed that scaling the learning rate of regular gradient descent type algorithms by the magnitude of the weights actually seems to improve the performance. So even though we're relying on these global convexity properties and the regret bounds intuition are somehow very different from what you'd see in non-convex setting, the final output actually produces something that seems to have reasonable dynamics. And so there's some hope that we'd actually get something good here. Nevertheless, there are some things that can go wrong, and I'm going to provide some motivation to see like what can go wrong and how we can try to prevent it. In a nutshell, the basic idea is that in convex problems, it's always possible to recover, right? You can't permanently screw yourself up when you're doing convex optimization. Even if you make a gradient descent step with learning rate 1,000,000, right? That's probably bad, but you'll end up somewhere very far from the optimal x star. But the gradient will still point you in the right direction, so it'll still tell you how to get back, right? You can always get home. In non-convex problems, this is not necessarily the case anymore. Not only that, neural network initialization schemes seem to be very important, right? There's these very carefully tuned ways to set up these networks to start with that seem to help in the optimization procedure. And we don't want to destroy this by making some very aggressive and perhaps bad early updates to our algorithms. So let me illustrate this with a picture. So I'm going to describe how parameter-free algorithms work dynamics on a convex setting, and then we'll see what could go wrong in the non-convex world. The motivation here is that parameter-free algorithms look a little bit like binary search. So let's start at some point x1. We'll make a small update to get to x2. Our distance between x1 and x2 is quite small, and that's because we don't have that much money yet, so we're betting very small amounts. But now we made some money, so we're going to make a bigger bet. In fact, remember that the wealth in the coin betting algorithms increases exponentially. And so we're going to grow very, very fast. It's almost like we're doubling each time until we reach some x4 out here. And now suddenly we're going to lose money. The bet will go bad. And since we made such a big jump and we bet quite a lot of money, we're going to lose a lot of money. And so we may end up losing, say, a third or a half of our money. So we'll end up at x5 here. And so what we end up doing is sort of doing a binary search to figure out where x star is, which is reasonable, right? That's a good way to, at least in this one-dimensional problem, to find x star. Of course, in the higher dimensional, in stochastic settings, we'll be doing something a little bit more complicated, but still, this is the intuition behind what's happening. Now, with binary search, you might think, well, why am I doubling every time? What if I tripled every time, or I multiplied by 1.5 every time, or something like that? And we all sort of have the intuition that that doesn't really make a big difference, right? You could increase by a bigger number every time, and then you would, maybe slightly faster overshoot the right thing and come back. But overall, you would save yourself a very small amount, right? It didn't take that many iterations for the smaller doubling factor to actually reach this x2 anyway. And you could, even overshoot the optimal thing immediately, and you'll come back very quickly. But overall, it doesn't really matter, right? You might save a little bit inside the log factors, but that's all that you're going to save by changing the search factor. On the other hand, for non-convex objectives, something very bad could happen, right? We could start quite close to the optimal point, but if we have a very large search factor, we could jump completely over some sort of local maximum and end up somewhere else. And then we could jump again, and we'll end up going really far away. So we'll have that in each iteration, we actually got worse rather than binary searching for the right thing, and we're never going to come back to find this value we were supposed to find initially, right? Even though our initialization was really good, we sort of immediately destroyed it and ended up somewhere quite bad. And that's something we want to avoid. So it turns out that in coin betting algorithms, the analog, the thing that sets the binary search factor, is the initial wealth. And we've been using initial wealth is equal to 1, just because that seems like the most mathematically reasonable default to use. But you don't have to do that, right? So if you make a small initial wealth, you'll make very small changes at first, and a large initial wealth makes for very large changes. On the other hand, right, the initial wealth, the wealth value changes exponentially fast, right? So in a convex setting where we have all our nice theory, we expect to be very insensitive to this value. And indeed, if you go look at how these papers work, the value is left as a variable, and you can see that the sensitivity is extremely low. However, in the non-convex setting, you cannot recover from bad variable, from bad initial values. So we might jump over the minimum value and end up doing something quite poor. So we need to be more conservative, perhaps, and sometimes start with a smaller initial wealth so that we don't end up making very bad, large updates at the beginning. So to start with, we sometimes need to decrease the initial wealth, although often that's not really necessary. And we're going to do one other heuristic trick, which is not that well theoretically motivated, to make things work, which is that we're going to keep the initial betting fraction from being too large initially. And this is also similar to preventing us from making large jumps in the beginning. So we'll take the true betting fraction, true beta, that we should be using, and we'll clip it to have magnitude at most 0.1 times the sum of the gradients. This 0.1 times sum of the gradients is motivated by the fact that usually the true beta value is set to be sum of the gradients times some multiplier in a lot of these algorithms. That's what it ends up being. It turns out that this multiplier, if you just look at it and look at what you expect it to end up being as the algorithm progresses, you expect it to be kind of small. And so what this is saying is that don't even bother doing sum of the gradients times something large, because you're going to end up with something small anyway. This is probably not the right final beta if you're just doing sum of the gradients times, say, 1, something like that. All right, so now I'll describe a couple other tweaks. All of these, I think, are fairly reasonable and motivated tweaks. So neural networks are not initialized to 0. So we need to deal with that, right? Because most of the algorithms that we've described so far are sort of naturally starting at 0 because you have maybe very small money at the beginning. So what we're going to do is we're going to record the initial value of the weights, and we'll just translate the optimizer's outputs by these values. So we just translate coordinates basically so that wherever we happen to initialize, it becomes the new origin. Then we'll normalize the gradients by the maximum gradient, so that overall we have this kind of pseudo TensorFlow code here, where both in TensorFlow or in PyTorch, if you're implementing an optimizer, you have to override some method that has a signature a little bit like this, where you take it takes as input a variable and a gradient, which is the gradient of the loss of that variable. And we'll compute the maximum gradient, we'll normalize it, we'll make some call to some parameter-free algorithm that we've implemented somewhere else that will give us the offset value. and then we'll get the initial value and assign the variable to its offset plus the initial value. Finally, one more tweak is we're going to add the average of the previous outputs, just like in the previous section when we talked about strong convexity adaptivity. So here the pseudocode becomes marginally more complicated. We compute the offset as before, but now we get this sum squared of the gradient, and we compute this weighted offset where we weight the tth offset by the squared norm of the gradient at the tth time step, and then we'll add the average of this weighted average offset to the offset we got from the parameter free algorithm to the initial value to get our final update for the variable. All right, so these are all the tweaks that we use. Before I actually give the empirical results, I'm going to describe the actual algorithm that we're using because it'll look a little bit different and have some different properties than the ones we discussed before. So in particular, we're going to be looking for a preconditioned regret bound. What does that mean? Preconditioned regret bounds look like the following. So we have the linear regret can be bounded by the square root of d times the sum of the inner products of gt and x star squared. This could be quite a bit better than the two norm bounds you've seen before in this tutorial, where we have norm of x star two norm times square root of sum of the two norms of the gradient squared. Because if we ignore the dimension factor here, this term is always better just by Cauchy-Schwarz. On the other hand, of course, with the d-dependence, it's unclear which of them is better. But nevertheless, you might say that, well, if the gradients have some very poorly conditioned covariance structure, this bound might be a GWIN. Unfortunately, algorithms that achieve this usually require some expensive matrix multiplications, and that ends up resulting in them being somewhat slower than just gradient descent would be. However, recent work has suggested that such algorithms are actually helpful in optimizing neural networks. If you ignore the computational complexities of running the algorithm, the iteration complexity can be quite good. And so you can see that it's making better iterates. And so we'd like to be able to make these iterates faster. And we'll see that we can sort of do this with coin betting. So using coin betting, we're going to provide an algorithm such that no matter what, we always have the same bound that we had before, this two norm adaptivity. But if the gradients have some sort of wonky property that I'm going to discuss in a minute, then we'll obtain this preconditioned regret bound. In fact, we'll do even better because we won't have a square root of d. There'll be no d here. So when this condition is satisfied, this bound is obtained, and it's always better than this bound. So what is this condition? It looks a little bit weird, right? It's saying the sum of the gradients is bigger than the square root of the sum of the gradients squared, basically. And if we think about, as a simple example, what would happen if the gradients were all just mean zero random variables? This is basically saying then that the sum of the gradients is violating something like Hufting's bound. And of course, that won't happen if the gradients are random variables. But if there's any signal at all in the gradients, we expect it actually to violate Hufting's bound because essentially Hufting bound is tight. So if there's any signal at all in the gradients, if there's any sort of systematic bias, we'll actually be able to satisfy this condition, and we'll obtain this better preconditioned regret. So not only that, the algorithm is actually fast. So it's going to run in the same time as SGD. So we make no trade-offs, right? We get basically the same thing that we were getting before, but just if the world is a little bit nice to us, we'll do something much, much better. So how do we do this? And we're going to have to generalize the coin betting framework to a vector setting. So we've previously been focusing on one-dimensional coin betting and then coming up with different ways to convert the one-dimensional algorithm to a d-dimensional algorithm. But then we don't have to do this. We can do coin betting directly on vectors. So we can define the wealth as just, say, initial wealth minus the sum of the inner product of g and x instead of the product of g and x. And then our betting fraction is beta is now a vector with norm at most 1, and we'll play beta times the wealth. So you should think of this as G being a vector of coin flips, or maybe a vector of sort of stocks, and beta represents the amount of money you're betting on each individual coin, or sort of your long and short positions on different stocks, something like that. With this framework, we would like to build a new second order regret bound, and we're going to use, instead of the online learning framework that we talked about earlier, we're going to use what I'm going to call parameter free inside parameter free. So in the previous section, we saw that we could get a nice regret bound by somehow learning beta t on the fly by thinking of it as an x-concave optimization problem. We could still do this in this vector setting, but unfortunately, it's not so nice. And that's because optimizing x-concave functions in high dimensions is actually slow. It requires, again, doing some matrix multiplications, and so we'd end up being much slower than SGD. So we're going to do something a little bit different. Instead, we're going to just sort of forget about the x-concavity, and we'll remember that the optimal beta star is usually very small. We can just compute it in many settings and see like, oh, actually it's going to be small. In fact, it'll usually be 1 on root t in size. And that means that if we just used a parameter-free algorithm to learn beta star, its regret would be beta star times root t, which is just 1. So that means we actually learn the optimal beta star quite fast. And if we do the sort of more refined analysis, we can show that, especially when this condition holds, we'll actually be able to learn beta star even faster in some sense, and so we get the preconditioned regret bound. So what the final algorithm actually looks, not that bad. We have sort of a inner optimizer A, which is some parameter-free algorithm. It could be using a one-dimensional algorithm with x-concave optimization that's been converted to a d-dimensional algorithm, but it doesn't matter. It could be anything else. We get some beta, vector beta from that algorithm. We play x to be beta times the wealth. Then we get a gradient. We define the analog of that log loss from the previous section, but now with a vector quantity instead. We get its gradient and we send that to A. And that's the end. It's the entire algorithm. We call it recursive optimizer because we're sort of using a parameter-free algorithm as a subroutine inside of another parameter-free algorithm. Of course, it's not really recursion. It's, but it's a similar idea. Okay, so what are the two lessons behind this recursive optimizer? The first is that having small regret for small comparators can be used in really sort of surprising and non-intuitive ways, right? We found some problem somewhere where the comparator we were looking for, beta star, was small, and that enabled us to get some very interesting gains. Not only that, the parameter-free algorithms actually can obtain better results than you would be able to obtain with any gradient descent method. I don't know of any way to tune the learning rate of gradient descent that gets the same results that this preconditioned parameter-free algorithm actually does. All right, so that's the end of the math here. Let's look at some actual experiments. So we trained the preconditioned optimizer recursive on several image recognition and language modeling architectures. We're going to compare to Adam and Adagrad with fixed learning rates. So, if you were just trying out of the box, you built some model and you don't have like a bunch of money to muck around training it, you're just going to try some algorithm. So you're going to sweep the learning rates on some logarithmic grid. That's roughly what we're doing here. I should note though that if you have the money to do some like very complicated tuning, you can do a more complicated schedule where you do maybe some linear warm up in the beginning for some unknown number of epochs, and then you do some polynomial decay with some exponent, something like that. There are more complicated things, and they will get better results than we'll show here if you do that. All right, so let's get started. Here is ResNet 50, which is a large image recognition model trained on ImageNet, which is of course a famous image recognition data set. Here we plotted the top 1 test accuracy. So this is just the test accuracy, basically, of Adam, Adagrad, and recursive. And here, the recursive optimizer is the winner, followed by Adam, and then Adagrad. The gap between recursive and Adam is roughly about 1%. So it's about a difference of 0.7 to 0.69 here. Transformer model is a large NLP model that we trained on the 1 billion words language modeling corpus. And here we have, again, the same story. Recursive optimizer is a little bit better than Adam, which is a little bit better than Adagrad. The gap may be slightly larger here. We also trained Transformer on the Penn Tree Bank dataset. So here, recursive and Adam are basically tied, right? There's not, I wouldn't say it's particularly clear which one's better. Maybe Adam is slightly better in the very beginning iterates, but it's certainly by the end, there's not really a difference. But both are significantly better than Adagrad. And finally, here is the BERT architecture for base pre-training. BERT is a really big language modeling architecture that's been seeing a lot of use lately. And this task is a little bit different, where you have a sentence that has been blanked out some of the words, and your objective is to predict what those words are. And here again, we have the same story we've had all the previous slides. Recursive is a little bit better than Adam, which is a little bit better than Adagrad. Okay. So the overall message here is that, recursive seems to do quite well. These parameter-free algorithms do very well, subject to these tweaks that I mentioned on these deep learning tasks. Unfortunately, however, I mentioned that sometimes we need to make sure the initial wealth is not too big. That's actually not that common. Most of these data sets, I just set the initial wealth to be 1, but occasionally that didn't work, and so I dropped it by an order of magnitude, and then things would work. But this does mean that there is a parameter there. Now, since the wealth changes exponentially fast, though, you might be able to hope that small values of the initial wealth are somehow not too damaging, and that fits with our intuition, right? We kept it small to avoid very bad initial updates, some bad instability in the beginning. If we make it even smaller, we would still not have that bad initial instability, but maybe the wealth will quickly grow to be the right value. So we can try to measure this robustness, and we'll compare to measuring robustness of Atom to the learning rate, because Atom is also, famously supposed to do well with, different learning rates. So here we have Atom trained on different learning rates on ResNet 50. The best one is up here, it's 0.69, something like that. If you drop the learning rate or increase the learning rate by a couple orders of magnitude, things are quite bad, right? You lose a lot of performance here. On the other hand, with recursive, if we change the initial wealth, if we make it 2 orders of magnitude too large, like this is initial wealth 100, then things are quite poor, right? But if you drop it by even several orders of magnitude, like 3 or 4 orders of magnitude, you see some loss, right? Somehow this one is, for some strange reason, magically better than everyone else, but all the other ones end up clustered around about the same point. And indeed, if we overlay these two plots, we see the best of Atom is slightly worse than the best of the recursive, but all of the other sort of undervalued initial wealths for recursive, they're all slightly better, or maybe about the same, as the second best learning rate for Atom. Meanwhile, we're very robust, right? If you take the sort of drop Atom's learning rate by another order of magnitude, things get significantly worse. Okay, so that's all I want to talk about in terms of the experiments on deep learning. But and we're getting near the end of the tutorial, but let me just mention that there are a lot of other nice topics here that we didn't have time to cover. So first, there's a thread on parameter-free learning with privacy. So you want to make some updates that somehow preserve privacy in your data, and you can still do this while being parameter-free. There's also some connections to variance reduction to show nice ways to adapt to, say, the smoothness parameters in variance reduction. And then there's also a really beautiful line of work on scale invariant learning, which we unfortunately did not have time to cover, but I highly encourage you all to look at. Okay, so finally, I want to conclude with some open problems. Here are a few. So first, I think the obvious one is, what can we say in the non-convex realm, right? We had to do a lot of tricks and tweaks here. Can we get something that's a little bit more principled or prove that there is no such thing? What can we say here at all? What if you're allowed only to query function values rather than gradients? This is the bandit feedback model. Is it possible to build analogous bounds? Or again, it might be true that the bandit setting is somehow fundamentally harder, and so you can't do it. And that would also be an interesting thing to prove. Third, and maybe more technically, we've been measuring our performance here using norms, right? We've said that, the optimal learning rate is the norm of X star, and our convergence rate is the norm of X star over root T. But maybe we could measure using some other non-norm function, like maybe moving only slightly away from norms. You could hope that you might be able to measure things in terms of a Brinkman divergence and still have some nice guarantees. Next, in stochastic settings, we might be able to do something better than in the online setting. So we mentioned that online learning is a sort of fundamentally harder problem. And also that in the online learning setting, there's this sort of lower bound where you might have this penalty G times the norm of X star cubed. But in stochastic setting, this doesn't really seem to happen. The adversary that produces this lower bound in online learning is pretty non-stochastic. It does some weird things. And so it seems plausible that you might be able to prove that if you leave online learning behind and just look at stochastic assumptions, that under reasonable assumptions, this sort of thing will not occur. And then finally, all the bounds we've shown so far have held in expectation. And I don't know of that many high probability bounds for parameter-free algorithms. I think this is a great thing to look for. All right, so this is the end of the section. Let me just summarize what we talked about here. So we mentioned that parameter-free algorithms work well on benchmark tasks, both in convex settings and even in non-convex settings if you do the right tweaks. Sometimes we saw that parameter-free bounds can actually exceed the tuned SGD bounds. So one way to intuitively think about this is that you could imagine a really awesome SGD that has a separate learning rate for each dimension, a separate learning rate for even things that are not necessarily dimensions, some other weird alignments, all sorts of different things. By being parameter-free, having no learning rates, we could sort of sometimes do as well as if we had tuned all of those simultaneously. And that's sort of the intuition I have for why we can sometimes exceed the tuned SGD bounds. Finally, there are a lot of good open problems to solve that I would really like to see some progress on in the future. All right, thank you.